In this next lesson, we are going to review logarithms and exponential functions. We are going to take a look at how they're related, and we're also going to talk about the constant e. So let's go over some definitions first. When we talk about the constant e, that is an irrational number, just like pi, it shows up quite a bit in science. When we look at this equation right here, this is written in exponential form. And this is saying if I take the constant e and raise it to some value of t, that will give us a. This a is called the argument, and the e is the base. So now let's look at our second form. If we rewrite this equation in a different form and we write it so our exponent is equal to the natural log of a, then we're calling this the natural logarithm because it's log base e. Because we're using our exponential form, we have a base of e. And then the exponent is what the logarithm of a is equal to. So we have a, that's our argument, that's here and here, depending on which form you're writing it in. And then t is our exponent, depending on which form we're writing it in. A, our argument, is always going to be a positive number. There is no real number that I can plug in for t that will ever give me a negative number, or 0. If I plug in 0 for the exponent here, I get e to the 0, which is 1. It's a positive number. No matter what I plug in for t, it's impossible to get 0. To show that this can never be a negative number, of course, we just showed that e to the 0 is 1. And e to a positive number would definitely be positive. So let's check to see what happens when I plug in a negative number. So let's say I have e to the negative 2. Well, let's remember what e to the negative 2 means. The negative 2 as the exponent means we're going to square the e, but the negative tells us to take the reciprocal. So we would have 1 over e squared. That's still positive. So if you have a negative in the exponent, all it's going to do is take the reciprocal, and since this isn't a negative in front of the e, it's never going to be negative. So a will always be positive. It will never be 0 or negative. Looking at this fourth note, we have t is equal to the natural log of a, and that expresses t as a function of a. Just like we say f of x is a function of x, this would be our dependent variable when it's in this form, when it's in logarithm form, and a would be our input, so this would be like our x. So you plug in something here, and you get something out here. So let's look at some examples of logarithms with different bases, because up till now we've only talked about base e. E is the natural constant, and so when we write it in logarithmic form, that would be natural log. Now, when we look at a log expression, the little subscript down here will tell you what your base is. So if I wanted to write log base e here with a natural constant, that's the same thing as the ln, because that's the natural log. You can write it either way. If there is no base listed as a subscript, then you can consider that what's called the common logarithm, which is going to be base 10. So just like we don't put a 1 always in front of our x, we know that it's 1x. Just like if we don't put a base here, we know that it's log base 10. Okay, so looking at these three examples, let's start here. If I find 3 and raise it to the 4th power, that's going to give me 81. The 3 is my base. The 4 is my exponent and the 81 is my argument. When I rewrite it in log form, since my 3 is my base, I would put that here. Since I know logarithms is equivalent to exponents, it's just a different way to write it. This 4 over here, that's the exponent, will be what this log is equal to. And then this is our argument, and so that's what we plug in to the log function to get the exponent. So 3 to the 4th, we get 81, which means when I take the log of base 3 of 81, I get 4. Now, let's look at an example with a negative exponent. Here's my base in yellow, my argument in blue, and my exponent in green. If I take 4 and raise it to the negative 2 power, that means I want to square 4, which is 16, and the negative tells me to take the reciprocal. So when I take 4 and raise it to the negative 2 power, I get 1 over 16. That's 1 over 4 squared. So when I rewrite that in log form, since 4 is my base here in exponential form, I'm going to put my 4 here as my base when I'm in log form. And 1 over 16 is my argument, and then what that is equal to is my exponent. Looking at the third example, you'll notice that I removed the negative sign here and here. I made a mistake and added that in, but I intended to write this as 1/2. So when you take 64 to the 1/2, remember 1/2 is another way to say square root, because the number in the bottom means, because the number in the denominator is telling us the root using our exponent rules. So 64 to the 1/2 means the square root of 64, which is 8. Now, when I rewrite that in log form, my base here in yellow is 64. My argument here is 8. That's what I'm plugging in. And then what I get out is my exponent, which is 1/2. Now let's look at converting exponential equations to the corresponding log equation. So when we look at part A here, we're going to use the same method we did on the previous slide. We're just now involving variables in our equations. So we have y is equal to e to the 2x. This is our exponential equation. If I want to rewrite that as a logarithmic equation, this is my argument, so I would put that here. I would use natural log because I have a base e here. I made sure that I reminded you down here that the base is e. ln is equivalent to the log log with base e. The exponent is 2 to the x, so I bring that down here. That's what is equivalent to natural log of y, because our logs are exponents. So when we write it in logarithmic form, we have to make sure that what is on the other side of the equal sign is our exponent. In the next one here, you'll see that we are using a base e again. So I want to note that we are using the natural log because that's log base e. A is the argument, so that goes here. And then 4x plus 3 is the exponent in exponential form. So we're going to set natural log of a equal to 4x plus 3. Last example, again, we have base e. That's our natural constant, so we're going to use natural log ln, or you could write it as log base e. 20 is the argument, so I put 20 here. And then our exponent is negative 0.3x, so I put that here. Now let's work in the other direction, where it's in log form, and we're putting it in exponential form. And if you notice again, we're using natural logs, so we're going to have base e. If this said log 5, then this would be a 5 here. Just make sure you're using the same base. Because the natural log of 7x is equal to 5, I know 5 is my exponent, so I put that here. And then 7x is the argument, so that's what it's equal to when it's in exponential form. We have the natural log of y minus 3. We're using natural log, so our base is e. That's our base here. What the log is equal to is x plus 5, so I know that that's my exponent. And then that's going to be equal to my argument. Third example, we have the natural log of x plus 8. We're using natural log, so I know my base is e. Since it's equal to negative 0.01, I know that that's my exponent when it's in exponential form. And my argument is x plus 8, so I need to set e to the negative 0.01 equal to x plus 8. For this example, we're going to look at evaluating some special cases. And this actually holds true for the log of any base, but we're specifically using the natural log here as our example. When we need to evaluate this, natural log of e is equal to question mark. This is what we're trying to solve. So when we evaluate this, since logarithms are exponents, we're really just looking for the exponent when it's in exponential form. So if I write this in exponential form, e is my argument, and because this is natural log, I know that my base is e, and I'm looking for my exponent. So this means I have my base is e raised to some exponent, and I get my argument, which is e. So the only exponent that will give us e when we raise e to that power is 1. This property works for any base. If the base and the argument are the same, then you're going to get this situation right here where you have the base raised to some exponent and that's equal to the value of the base. So in all cases where the base and the argument are the same, the answer is going to be 1. Now, here's another special case, and this holds true for logarithms with any base. This is asking us to evaluate, which means find the exponent, because this is log, what my exponent would be if I take my base e, raise it to that exponent, and get out 1. So here's my base e. I'm looking for the exponent that gives me the answer 1. The only number that will do that is 0. When I raise a constant to a 0, it gives me 0. So this holds true if you're taking the log, no matter what the base is, of 1. So the log base 7 of 1, the log base 100 of 1. Whenever you see the log of 1, you know that's going to be 0. Now we're going to look at the properties of the natural logarithm. Just keep in mind that these properties apply to all logarithms. The book is choosing to focus specifically on the natural logarithm, but these rules do work for logs of any base. So number 1 and number 2, we just talked about those. We just talked about those in the previous slide. If the base of your logarithm and the argument are the same, then that's going to give you an exponent of 1. For property number 2, no matter what the base is, when you take the log of 1, it's going to be 0 because you take a base and you raise it to the power of 0 every time you're going to get 1. This property right here with number 3 is a specific case of this property number 6. So I want to look at number 6 first, and then we'll backtrack to property 3. The property in number 6 is stating that if you have a logarithm, it doesn't matter what the base is, and your argument is raised to some power, you can rewrite that as an equivalent statement where you bring that exponent, in this case we're calling it r, and we bring it down in front and multiply it by the logarithm. This seems a little bit weird, but don't forget that logarithms are exponents, and so this is just a variation of an exponent rule. If you're interested in seeing the proof for that, let me know and I can show you any of the proofs for property 4, 5, and 6. All of those stem from exponent rules. So now that we've looked at property 6, let's go back and look at property 3. This is a special case of property 6. The reason why this is a special case is because we have the natural log of e, and this natural log has a base of e. So we're in this situation right here where the natural log is equal to 1. But we're also using the fact that because our argument has an exponent, we can bring that exponent down in front using property 6, and then I have x times the natural log of e, which is 1. So I have x times 1, which is x. If the base of your log and your argument are the same and you have an exponent, then you're just going to be left with that exponent. Okay, properties 4 and 5. Again, these both stem from exponent rules. Number 4 stems from the product rule with exponents. The product rule with exponents says if you have the same base and you're multiplying, then you want to add your exponents. So if I have the natural log of a product, then I can rewrite that in an equivalent form as the sum of the natural log of x plus the natural log of y. Number 5 stems from the quotient rule in exponents, where if you are dividing two numbers that have the same base, you want to subtract the exponents. So if you have a quotient in here, you can rewrite it as two separate logs with a subtraction. Now, this one here, the order doesn't matter. If I write natural log of y plus natural log of x, that order doesn't matter because addition is commutative. But when we're dealing with the quotient rule here, we want to make sure that this first term is using the top argument, the argument that's in the numerator, because here order does matter. So this argument on the top should come first here, and then the denominator argument should come second. That should be the second term. Let's practice using these properties so that we can get familiar with them. And the reason why we have these properties is because when we go to solve an equation that's exponential or a logarithmic equation, we can use those properties to manipulate the equation so that we can solve for the variable. Example A. So we have the natural log of 3x. Now this question wants us to expand the expression. So for example, if I ask you to expand 3 times the quantity of x plus y, that means we're going to rewrite it as multiple terms instead of keeping it as one term. So we would have 3 times x plus 3 times y. That's my example of what I mean by expanding. We're writing it in multiple terms. This here, the natural log of 3x, is considered a condensed form because it's all combined into one term. So using the product rule, I'm going to rewrite this as the natural log of 3 plus the natural log of x. If you want to evaluate the natural log of 3, you can do that on your calculator and get a decimal approximation. Unless the question tells you to give the decimal approximation, I would just leave it as natural log of 3. It saves you a step of having to do that on the calculator. You're not worried about having rounding issues because this is going to be a rounded value. For part B, we're actually going to be using two properties. We're going to use the quotient rule first because we have this division here, and we're going to take the top and subtract the bottom. And then if you look at the numerator, This term is also a product, so that's when we're going to use the product rule to create multiple terms for this argument. So we're first going to rewrite this expression using the quotient rule. And remember, when we're using the quotient rule, the order matters because we're subtracting. So I'm going to take the natural log of the numerator argument, and I'm going to subtract the natural log of the denominator argument. But we can expand it even further by making this two different terms using the product rule. With the product rule, because we're adding, the order doesn't matter. So for this one here, I'm going to take the natural log of 8 and I'm going to add it to the natural log of x. So this is the complete expanded form. Okay, let's look at part C. We have the natural log of x to the 6th. When we have something involving exponents and we want to expand it, we would use the power rule and bring the 6th down in front. So we have the natural log of x to the 6th is equal to, we would bring the 6 down in front, and that would be 6 times the natural log of x. For part D, we are going to start expanding this term by using the product rule. Because we have a constant out front here, we just need to make sure that we carry it down with each step. The other thing is, when we split up that logarithm into multiple terms, this 12,000 is being multiplied by the natural log of x times y to the 5th. So even though we split this up, that 12,000 should be applied to all terms because all of those terms are going to be equivalent to this natural log of x times y to the 5th. So when we apply the product rule, we're going to split the natural log of x times y to the 5th into the natural log of x plus the natural log of y to the 5th. Because this expression right here is equivalent to this condensed version, we still have to make sure that we apply that 12,000 to both terms. Okay, now that we've used the product rule, we're going to use the power rule to bring this 5 down in front. So that 5 is going to come down in front, everything else gets carried down. If you want to take this even further, you can just distribute that 12,000. Now for example 5, we are going to work backwards. In the previous example, we had one single term and we expanded it into multiple terms using the properties of logarithms. Now we're going to work backwards and we're going to take multiple terms and combine them into one. So looking at example A, we have two terms that are separated by a plus, and we also have this 6 here that we can bring up so that it's an exponent for y. Now, when you're condensing, you need to make sure that if you have a constant in front of the log and you need to bring it up as an exponent, that's the first thing that you do. Looking at this line right here, the natural log of x is carried over, and the 6 now comes back up as the exponent for the y. And now we can use the product rule to combine it into one term. So because this is addition, we can change the arguments into a product and list it as one logarithm. So this can be rewritten as the natural log of x times the natural log of y to the 6th. Part B, you have to be careful. You have to make sure you maintain the proper grouping. So don't skip on writing the parentheses. It doesn't matter which way you group them to start with, but I like grouping the first two terms together first, because if I group the second two terms and I put parentheses around these, around the natural log of b and the natural log of c, then I would need to change this subtraction sign into a plus. If I put my parentheses here and here to group them, then this should be a plus. So when I multiply it back out, I get the same thing. If I don't change that to a plus, then it's not equivalent. So be careful when you start grouping things. Make sure you ask yourself, if I multiply this back out, am I going to get the same thing? So that's why my preference, just like the author of the book has set up here, my preference would be to use the first two terms, and then I don't have to worry about that. So if we group these, if I remove the parentheses, it's the same thing. So we group these first, and then we subtract the natural log of C. Because we have a subtraction here, we can use the quotient rule. Natural log of A minus natural log of B first. Because these are being subtracted, I'm going to use the quotient rule. So I'm going to combine these two terms into one term. So this argument here, the A, will be in the numerator. This argument B will be in the denominator. And then we carry down the minus natural log of C, and then we can repeat the quotient rule one more time because I have two logarithms separated by a subtraction sign. The C, because this is the second term, the C is going to go in the denominator. So now I have the natural log of A divided by B times C all in the denominator. To this expanded form, we just condensed it into one term. So now let's look at the graph of the natural logarithm. So we have some properties listed out here. The first property says as x increases, the function increases, but it does so at a decreasing rate, meaning it's going to increase as t increases, but it's going to increase more slowly over time. And property 2 says if your value of x that you plug in for the natural logarithm is between 0 and 1, then the natural log is going to be negative. If you have x greater than 1, then the value of the function is going to be positive. We talked about this property previously, but now we're going to relate it to the graph. If I take the natural log of 1, I'm going to get 0. And you'll see that that's a point on the graph. I plug in 1, I get out 0. Lastly, the domain for the natural logarithm is, and for any logarithm I should say, is all positive numbers. It can't be 0 and it can't be negative. Now let's look at the graph of the log function and we'll compare it to the properties we just discussed in the previous slide. All log functions, no matter what the base is always going to have this shape. It's going to get really close to the y-axis because there's a vertical asymptote here at x equals 0. And then as we come across, we get this curve. And property number 1 describes how the function increases. The entire function, if we trace it left to right, is increasing. But notice we are almost going straight up here. And then as we go left to right, we're still increasing, but we're increasing at a slower and slower rate. So looking at property 2 now, for the values of x that lie between 0 and 1, the function is going to be negative. So if we look at any value of x between 0 and 1, it's going to fall below the x-axis. This is my x-intercept, and everything between 0 and 1 is below the x-axis. Property 3 says that when you have values that are greater than 1 for x, the function is going to be positive. So here's one, our x-intercept. If we look at values of x that are greater than 1, it's all above the x-axis, so all of those values are going to be positive. Property 4 references the x-intercept. When I plug in 1 for the function, I'm going to get out 0. It's the value of x when y is 0. That's our x-intercept. Property 5 describes the domain of the log function. The domain are all the values of x that you can plug into a function and get out a value for y. So when we look at the set of all the x values that create this graph, we have a vertical asymptote here, which means the curve is going to get really close to the y-axis but never touch it. So 0 is not included in the domain. The function increases without bound in the positive direction horizontally unbounded. So the domain for a log function is going to be from 0, not including 0, to positive infinity. So let's do a quick review of inverses because we're going to discuss how log functions and exponential functions are inverses. So in general, when we talk about an inverse in mathematics, that means we're just swapping the x and the y values. And another way to look at it is not just that we're switching the x's and the y's, you can think about it as one function undoes the other function. So, for example, the cubed root of x has an inverse that is x cubed. If I plug in 2 for x cubed, my output is going to be 8. But then if I use the output and plug it into the inverse, I'm going to get out 2. So it reverses those values. Now, when we look at log functions and exponential functions, and we know that they're inverses, the same rule applies. All our x's and our y's get swapped. So here is the exponential function 2 to the x. It's increasing because the base is greater than 1. And I listed some points here and I put them in the table. If I plug -2 in for this x, that means I square the 2, but the negative means I flip it upside down. So I plug in -2 and I get out 1/4. If I plug in -1, that means I raise 2 to the first power, and the negative means I take the reciprocal. So I'm going to plug in -1 and get out 1/2. If I plug in 0, 2 to the 0 is 1. So I get the point 0, 1. And then the same thing goes for these here. With exponential functions, if my base is 2, then the inverse is going to be log base 2. These bases should be the same, and if they are the same, then they're going to be inverses. So that means on the graph of log base 2x, I'm going to have this point but reversed. So I'm going to put the 1/4 in for x and the -2 in for y. So all of these points get reversed. Now when we graph the log base 2 function, this is the picture that we have. And this definitely looks symmetric about the line y equals x. If I imagine y equals x coming up through here, it's a mirror image across that line y equals x. And that's what an inverse should look like. They should be mirror images across that line. So on the log function, here's my point, 1/4 at -2. So over here, I'm going to have the point on the inverse, -2 1/4. So if I asked you what is the inverse of log base 3, right away you should be able to tell me 3 to the x. Exponential and log functions are inverses as long as the bases are the same. Now let's compare some of the behaviors of the exponential function versus the log function, and we're using base 2 again. So I have 2 to the x in purple, and I have log base 2 in pink. So we know that these are inverses, which means we know that the x's and the y's get swapped. We said a couple of slides ago when we were looking at the properties that the domain of the log function is 0 to infinity, not including 0. So that's this graph right here, the graph of log base 2. It never touches the y-axis because there is a vertical asymptote there. So it's from 0, but not including 0, to positive infinity in the horizontal direction. So my domain for the log function is 0 to infinity, which means because we swap our x's and y's, that will be the range for our exponential function. The range of the log function is from -infinity to infinity, right? Looking at it vertically, it goes down forever this way. And then even though it increases slowly, it's still increasing. So it's going to go to positive infinity in the vertical direction. So my range is going to be from minus infinity to infinity, which means the domain of the exponential function is going to be from minus infinity to infinity. When we look at the log function, we see that there is a vertical asymptote at x equals 0. That means there is an asymptote on the exponential function that's y equals 0, again because we switch x and y. So these properties here we looked at in detail, but now let's compare what we found by switching x's and y's to the graph of the exponential function. So looking at the graph of 2 to the x, we said that the domain would have to be negative infinity to infinity because that's the range of the log function. So if I scan this graph left to right to find all the x values, it's going to be negative infinity to positive infinity. And although this comes out slowly, it is going to keep coming out horizontally forever. The range of the exponential function is from 0 to infinity. There is a horizontal asymptote here at y equals 0, so it's not going to touch y equals 0, but it's going to go on forever in the positive direction, unbounded. So my range is going to be from 0, not including 0, up, unbounded in the positive direction. So you can see how all the x's and the y's get swapped. Now that we have reviewed logarithms and exponentials, we understand the properties, we know how to evaluate them, and we know what the graph looks like in the properties. Now let's apply all that knowledge to solve equations that involve exponential and logarithms. So we're going to start with this equation that says e raised to the exponent of 2x plus 5 is equal to 12. This is where the properties of logarithms come in handy because as it stands right now, I don't know how to get that x out of the exponent so I can isolate it. So now we can use the property of logarithms to rewrite that exponential equation in terms of logs. Because my argument is 12 and my exponent is 2x plus 5 and my base is e, we can rewrite in log form. I know if I want to rewrite this in log form because my base is e, I'm using the natural logarithm. Here's my argument. So I have the natural log of 12 and my exponent is what it should be equivalent to. So I just used the definition of a logarithm to rewrite and skip this step. However, we can take a look at this step and see what happened in between. The author of this book chose to look at this in a different way. The author chose to take the natural log of both sides. Remember that when we're dealing with equations, we can do whatever we want as long as we do it to both sides of the equation. So he took the log of both sides. So now we have natural log of e to the 2x plus 5 is equal to natural log of 12. And if we look back at our properties, we had a property that said if our base of the log and the argument is the same and there's an exponent, then that would simplify so that it's just equal to the exponent. If you want to look back at that, look back where it says the properties of the natural logarithm, and that would be property 3. Now we have x out of the exponent, and we can just solve this like we would any other equation. Keep in mind that the natural log and 12 have to stay together. You can't divide by log, ln, and cross them out. These two are stuck together. The natural log of 12 represents some value. We might not know what it is off the top of our head, but this represents an actual number. So if I imagine that this natural log of 12 is just some number, like let's say just to make something up, 7. To solve for x, I would subtract 5 from both sides and then divide by 2. So I have to treat this like a number. So just like any other number, as if it were 7, I'm going to subtract 5 from both sides. But because I don't know what that is offhand, I'm just going to leave it as the natural log of 12. So we have 2x is equal to natural log of 12 minus 5. And then to finish solving for x, we divide both sides by 2. If you want to keep the exact value, you leave it like that. If you need to round to a certain number of decimal places, you would put that in your calculator and find the approximated value. Just remember to make sure if you have a numerator that has multiple terms in it, you want to put parentheses around it to make sure that your calculator maintains the order of operations. In example 7, we have an application. It says the radioactive isotope uranium-235 decays according to the exponential decay model A equals A naught E to the negative KT. This can be called A naught, or if you're not comfortable with that, you can just call it your initial value. Remember, the initial value is always the coefficient of your exponential function. So if we go on here, it just describes that. A naught is the amount of uranium that is initially present. A is what's left over after T millions of years. And K is the decay constant. So this K here will tell us how fast it decays. Part A of the question says the half-life of uranium is about 700 million years. Use this information to calculate the value of the decay constant. So here's the information that we know. 700 million years is the half-life. That means after 700 million years, half of what was started with is going to be left. So that means whatever I start with here, we can just call it A naught. We're going to have half of it after 700 years. So we're going to plug in 700 here. That will allow us to solve for K. We really don't need how much we actually started with, because what's going to happen is when we simplify this, I can divide both sides by A naught and get rid of it. So we don't even really need it. So what we're left with is 1/2 is equal to E to the minus K times 700. So now we have an exponential equation and we can use logarithms to solve. Using the method that the author prefers, we take the natural log of both sides. So I put a natural log here and a natural log here. So now I have natural log of 1/2 minus natural log of E to the negative K times 700. I can bring the negative K times 700 down in front using the power rule for logarithms. And then I'm left with negative K times 700 in front here times the natural log of E. And we know that the natural log of E is equal to 1. So we have negative K times 700 times 1, which just gives me negative 700K. So I have negative 700K is equal to the natural log of 1/2. So to solve, we just divide both sides by negative 700. So when I divide by negative 700 here, I'm just left with K. When I divide by negative 700 on this side, I'm left with natural log of 1/2 divided by negative 700, and that's equivalent to the K. Now, when you're dealing with rates of decay, it's usually going to be a really small number. So you want to be careful and pay attention to how you should round if the direction tells you. But what I would personally suggest is to just leave it as exact and store it in your calculator. That way, when you go to work on the second part, you just stored it exactly and you don't have to worry about rounding errors. Now, if we look at part B, it says use the model with the newly calculated value of K to determine how many years it would take for a particular quantity of uranium to decay to 90% of its original amount. So now that we know what the value of K is, we put that in up here for K. And again, we really don't need in this situation to know what the initial amount is, because if we call the initial amount A naught and we want to know what 90% of A naught is over here, we're just going to divide by A naught on both sides and get rid of it, and we don't really need it. So what we're left with is 0.90 is equal to E to the minus 0.00099t. We can take the log of both sides, so we get the natural log of 90 is equal to the natural log of E raised to the power of negative 0.00099t. Because of the power rule, my exponent can come down in front, and then I'm left with my exponent times the natural log of E, and we know that the natural log of E is 1. So all we're left with on the right side is minus 0.00099t. So to finish solving for t, I just have to divide both sides by negative 0.00099. And when we do that, this is what we have. And then we calculate that on the calculator and we get an approximation for t. Now, this is where I tell you to be careful, because when you're dealing with really, really small numbers or really, really large numbers, the answer is going to be sensitive to rounding. So this is where I wouldn't actually put that decimal in on my calculator. I would plug in the exact value that we found right here. Instead of putting in the decimal value, I would put in the exact value here and then round the final answer. And that would be rounding just once. If you round this answer and then you round the final answer, it might throw your answer off enough that it's not going to be as close as you think. So what this represents is 106.4 million years. Remember, in the beginning of the question, it says that time is in millions of years. So in order for uranium to break down and so that only 90% of it is left, so that basically it decays 10%, that takes approximately 106.4 million years. Example 8 is another application. We have a piece of equipment depreciates according to the function A equals A naught E to the negative 0.32t, where t represents the number of years since its purchase. A hospital purchased a piece of capital equipment for $635,000. It will replace that piece of equipment when its value is 10% of its purchase price. To the nearest year, how many years will the hospital own the equipment? So here's the function given. We know that the initial amount of the price is $635,000. So that's what we need to put in here for the initial amount. The question wants us to find how long it takes, meaning we need to look for t, until it is down to 10% of the original price. So we want the output to be equivalent to 10% of the price. So if we find 10% of 635,000, we get 63,500. So that's what we want to set it equal to. So here's what we started with. It decreases to 10% of the original amount, and we need to find that value of t so we know how long it takes to do that. Now, we could completely skip all this part. Since we know that it's 10% of the original price, we can skip all this stuff without actually having to put the values in, and we know that what's on the left here is going to be 0.10. because when we divide both sides by that A naught, all that's going to be left with is 0.10. So imagine you have 0.10 times A naught, the initial value, is equal to A naught. Just divide both sides by A naught, and you're left with 0.1. So this is equivalent to 0.1. And then on the other side, I have e to the negative 0.32t. So now if we take the log of both sides, we get the natural log of 0.1 is equal to the natural log of e raised to the negative 0.32t. The natural log of e is 1. This can come down in front. So what we're left with is negative 0.32t. And when we put this in on the calculator, all that's left is we need to just divide both sides by negative 0.32 and then put it in the calculator and find an approximated value. When we approximate this and round it, we get 7 years. So it's going to take 7 years for this value to depreciate to 10% of the original value. So here are your conceptual questions for the end of the lesson. When you've completed the homework, try going through and answering these questions.